So collision theory is the why of chemical reactions. So to have anything react, they have to come into contact, and they have to come into contact with enough energy and also in the right orientation in order to react. So when we're talking about rates, and I mentioned this Tuesday, but when we're talking about rates, the reason that the rate of a reaction decreases over time is because we're reducing the number of particles available to react. Right? As those get used up, the likelihood of a collision goes down. And so that's why I put also on Canvas, there's that more about collision theory sort of goes into it. I don't remember what the size of the container was, but it was not a very big container. I think it was like a 1 milliliter cube. If you had a gas and two gases reacting in there, or even just a gas in there, there's like 10 to the 33 collisions per second or something crazy. So there's a lot of collisions that are happening, but not all happening with the right amount of energy. And then gas molecules too will have a wide distribution of velocities, so wide distribution of energies. So if we wanted to increase the rate of the reaction based on collision theory, there are actually three things that we can do. Does anybody know what those three are? Or just one of the three? Huh? Raise the temperature, right? If we increase the velocities of those particles, we increase the amount of energy. More of those collisions result in reactions. What's another one? Pressure. Pressure would do it for gases because we're increasing concentration. So the number of gas particles is what determines the pressure. So if we increase the concentration of our reactants, we'll also speed up the reaction because now there's more particles, more collisions, more likely to, it's all about statistics, more likely to undergo a reaction. What's the third one? Mixing can help. Depends on the solution. The third one I'm looking for actually is a little bit trickier, but adding a catalyst. All right, so if you decrease the amount of energy required for the reaction, then more of those collisions will hit that barrier or go over that barrier to react. And actually, I found a really cool, I've been looking for a demo like this. Oh, I might have to reload it, and it's going to take a while. Nope, it just told me forbidden. Cool. All right, never mind. I didn't find a thing. I'll share it later if I can get it to work. It basically just gives you a visual, though, of what it looks like when you have particles flying around in a box, and it lets you play with some parameters like temperature, the number of particles, that kind of thing. Okay. All right, so again, this is all going to be, or a lot of this should be review, but most chemical reactions have activation energy, right? So that's why we can increase the temperature, add a catalyst, those will speed up our reaction rates. And we'll actually talk about how this activation energy in the Arrhenius equation relates to reaction rates. And we'll see actually the math to be able to calculate that. But yeah, anything that affects the rate of anything that affects the rate of, the factors that influence the rate of reaction are the same factors that affect the number of high energy collisions that occur per unit time. Those things are directly tied together. I think I just copied these over from another one. All right, so more collisions, higher temperature, more collisions. There you go. So reaction rates generally increase with increasing reactant concentration. We'll actually see there's one scenario where that doesn't happen in terms of reaction order. They also generally increase with increasing temperature. And actually, as a rule of thumb, reaction rates double. You can double the reaction rate for every 10 degrees C that you increase the temperature of a reaction. And then reaction rates generally decrease as the reaction proceeds because, again, we're using up the reactants. And I'll re-upload all of these slides again so you'll get them with these new ones in there. All right, that brings us to where we left off then. So the rate law shows the relationship between the reaction rate and the concentration of the reactants. So how fast exactly, or at all, does the reaction rate decrease according to concentration? In here we've got a constant, the rate constant, oops, K, and N is the reaction order. So that order is what's going to determine how fast or how much our concentration matters to the reaction rate. For a zero order reaction, the rate is independent of the concentration of A. For a first order reaction, the rate is directly proportional to the concentration of A. So if your concentration decreases by half, your reaction rate decreases by half. Right? It happens at the same rate. For second order reactions, the rate is proportional to the square of the concentration of A. So now instead of just, if we have a reaction, second order reaction, and our concentration goes from, let's see, I'm just going to put a number in here. The concentration goes from 2 molar down to 1 molar. How much is our reaction rate going to change? If we decrease by half, it'll be a quarter. Yeah, so it'll be however much it changes squared. Or the magnitude, the ratio squared. And other orders are possible. And actually, if you get out into the real world, orders higher than that are really, really, really unlikely. So if you think about, again, let's tie this back to collision theory, especially for a second order reaction, what that's saying is the reaction is dependent on the concentration of two separate things colliding. So if we have a reaction like I2 plus H2, 2HI, this is an example of a second order reaction. Because if the concentration of I2 decreases, then we're going to have fewer I2, H2 collisions. But if the rate of, and the concentration of hydrogen 2 will do the same. All right, so anything that's decreasing the number of reaction collisions is going to decrease the rate. Why do you think it would be really unlikely for to have a third order reaction? What would have to happen in a third order reaction? You can write out it. Yeah. You have to have A plus B plus C to make ABC. So you have to have a collision where all three particles collide at the same time with enough energy to react. Usually what happens instead is there will be an intermediate step. So you just have to have A and B collide, and then later they have to get hit by C. And so you'll have actually multi-step reactions. Again, we'll talk about that more, right? So collision theory is at work here too. Actually, we'll talk about zero order in a second. Zero and first order. So if you're to plot these out, let me write these equations in too. So for a zero order, right, that's K, and then the concentration of A raised to the 0. And what is anything raised to the 0 power? It's just 1, right? So our concentration in a zero order reaction doesn't change the rate. So we can look at the, zoom on this, the concentration of A here is decreasing over time, but it's doing so at a straight line. And what determines the slope of that straight line? If I guess here we're starting at 1, so we can say plus 1. So the rate law is in a format that is plottable as a linear equation. So the slope of this line is k. And that's the only thing that determines the rate of that reaction. It's not changing over time because, the slope here is k. And then x in this scenario is the concentration raised to 0, so it's just 1. So it's not changing as that concentration changes. And then if we take the derivative of these lines, right, and we just look at the rate as the concentration, actually it's not quite the derivative of these lines, is it? But if we look at the rate as a function of the concentration of A, 0 order is just a straight line. So then when we move over to our first order reaction, now instead of just decreasing at a constant rate, we're actually decreasing at, well, the rate is decreasing over the course of the reaction because now it's K times A to the 1. So every time we lose some of that concentration because it's reacting, that slope gets shallower and shallower and shallower. And then if we look at the second order reaction, that happens even faster because now it's not just reducing by A, but A squared. So one example of a 0 order reaction, and really any scenario where you have a 0 order reaction, is if you have so much of the reactant that the concentration isn't changing. And so one of those scenarios is if you have like dry ice subliming. Even though you are losing some of that dry ice, the amount available is only determined by the surface area of the dry ice. So over a long, long, long period of time, that rate might change. But there's always going to be CO2 on the surface replaced by the CO2 under it as it sublimes. So then that rate stays the same. For a first order reaction, the rate is directly proportional to the concentration of the reactant. So the rate slows down as the reaction proceeds because we're decreasing the concentration. One example of a reaction example of this, something like H plus, and I should write aqueous, plus H2O So for this reaction, imagine we've got a beaker and that's full of water. There's some H plus in here. How do I want to word this? Well, I guess so. There's some H plus in there, but there's so much H2O that any amount of H plus that's in there reacting with H2O doesn't change the concentration of H2O. Right? Because the concentration of the concentration of pure water is 55 molar. But the concentration of H plus in any solution of acid is going to be something like, 1 times 10, and really on the high end, 1 times 10 to the negative 3 molar versus the 55 molar. So even as that H plus is reacting with the water, the concentration of the water doesn't change. So it doesn't have any effect on the rate, but the concentration of the H plus will decrease noticeably, and that will be the only thing affecting the way that reaction slows down. For a second order reaction, this is actually the most common order of reaction. I guess we haven't quite gotten to, but this is where the concentration is dependent on two separate things having to have that one collision. So again, you can use this example of H2 gas plus I2 gas forming 2HI gas. So the rate of this reaction is going to be sensitive to the concentrations of both of those species. And so as we're losing those, right, our reaction rate is going to decrease even less. It's going to decrease even faster. Any questions? We'll get to how to use this a little more. So for a particular reaction in which we have one thing, A, one reactant being converted into products, if we do an initial rate reaction and we see that doubling the concentration of A causes the reaction rate to double, what is the order of the reaction? First order. Yeah, because if the concentration of A goes up by, or doubles, concentration of A times 2, then rate will also increase times 2. So first order. And we would write that out as rate equals K times A. So the reaction order, and I've shown you some examples, those have been determined by, well, actually for those ones, the reaction order can be determined only by experiments. So somebody had to do experiments to know that those things were first order or second order reactions. We can now like think about them as like once those have been determined to be the case, you know, like apply collision theory and say like, oh yeah, collision theory explains this. It lines up with the conceptual model. But the way that you do this is the method of initial rates. So you set up a reaction with some concentration. So if we've got our unimolecular reaction of A being converted into products, we set up a reaction, we put 0.1 molar in our flask, and that reaction starts. And then we'll measure just maybe the first, depends on how fast the reaction goes, but let's say like the first 5 minutes. So what is the rate in those first 5 minutes if we start with a concentration of 0.0 or 0.10? And then we set up another reaction, right? We've recorded that rate, set up another reaction, and then we double the concentration. So let's put twice as much A in, and then observe again, first 5 minutes, how fast does that reaction rate go? This is what you were doing with the, well, you kind of did this with the calcium carbonate chips, right? If you have that big chip, you put the big chip in, you can measure that rate. It's a similar type of experiment. So then you can double it again and you can get another initial rate. And then we can see, just like we did on this previous problem, how the concentration changes and how the reaction rate changes. So for this reaction, if our first one is 0.10, our rate is 0.015, we double it, it goes up to 0.030. So what is the reaction order for this reaction? 1. So a reaction order with respect to A, which is the only element we have in here right now, but the only reactant we have is first order. Okay, so you just write first. And then with that reaction order expression, or the rate expression, oh, sorry, not the rate expression, because that's the other one. The rate law, there we go. Right, the rate is equal to K, A, and I'm going to put the first here, just for now, just on this one. Right, so if we have the rate, which we have from our experiment, and we have the concentration of A that gave us that rate, we can plug those numbers in and get K. So rate was 0.015 molar per second equals K times concentration of A Oh yeah, I should be able to do that. 0.15 1 over seconds equals K. Yeah. Yeah, you could also put seconds to the -1. And actually, on Alex, so the problem that I told you about that had an issue, it was this kind of problem. It was calculating K from a table of rate experiments, initial rate experiments. So the way to get around it, the way to avoid that problem is always use the first entry. So what I mean by the first entry, always use this sort of first line on their table of data, and you'll get the right answer. And it just comes down to rounding stuff. So like my answer that I put in there was 0.741, and it wanted 0.743. And then of course I went to an Excel spreadsheet and I typed in all the data and did the calculations like that. And I mean, it's just, they're all very close. Some of them are more egregious than others, but in the real world, we could use this first entry to calculate K, we could use the second one, we could use the third one, because K is a constant for this reaction, right? So it doesn't matter, shouldn't matter, which data we use from this experiment. We'll still get the same K. And these are like within experimental error of each other. Those should both be acceptable answers. And we'll say on an exam or an assignment that I'm grading, those would be acceptable, like within an acceptable limit. Okay, any questions on this? Because it can get a little more complicated. So we can determine, actually I'm gonna skip over to this Alex problem I have written down. Because I wanted to go over the math. Okay. Just realized the problem with doing this is now. Sorry. I came up with this like 10 minutes before because I did that problem. So let me write this. Okay, you know what? Better yet. So this is the type of problem. And what I want to show you actually is just how to get to how to solve for A using the equation that's on these slides. So, right, it says if it's too hard to figure out by just looking at it, because it's not always going to be this thing, we doubled this concentration exactly, and then, you know, very cleanly doubled the rate or quadrupled the rate. It's not always going to be that easy to see. So you can set this equation up because it's going to be the ratio between the two that determines what your rate order is. So if I take this and I clip it, we go to this next slide. What you have to do with this is solve for n, right? If we want the rate order of this reaction, and we have to solve for n. And that involves some tricks with logarithms. So does anybody know what you would do first in this problem to try and isolate n? Cancel some stuff. We can cancel the k's, right? The k is going to be the same for those. So yeah, that does simplify things. Oops, I said k, so I wrote k. Rate 1, now concentration of n, A1. Oops. N, right, because the rate or the order for this reaction will be the same, but the concentrations and the rates are actually going to change because the concentration is going to be dependent on the rate. So the first trick that you have to use here is that is a trick with logarithms. So you can use the natural log or you can use log base 10. It doesn't matter here. If we take the natural log of both sides, I'm just going to do the natural log because it's easier to write. Rate 2 over rate 1. Can I redo that, please? Okay. Rate 2 over rate 1 equals natural log of concentration of A1. Oh, sorry, A2. I flipped these. A2, A1. If I take the natural log, now, this is just what is a rule? It's a rule of logarithms. I can take this n, since these are both raised to the same n, and now it's n times the logarithm. So we can pull that out of the log. So n times the natural log. Is everybody okay if I replace these with x? That'll speed things up here a bit. This is going to be R2 over R1. So now we've got n here multiplied by this. And so we can actually just take both sides and divide by the natural log of x2 over x1. So we'll get the natural log of R2 over R1 over the natural log of x2 over x1 equals n. So if you haven't gotten to this problem already in ALEKS, this will help a lot. There's some other property. That was the word I was looking for earlier. It's a property of logarithms. Any questions on that little derivation? Logarithms will come back up again. Okay, so everybody got that written down? All right. So, actually, I'll go back to this one. Right, the units of m, or the units of k here, dependent on, well, they come out of the fact that we took this, or we divided our rate here by the concentration, right? So if we have, this is molar per second, and this is molar, so if we divide by molar, we get 1 over seconds for the units for k. But what if we have a second order reaction? Or even a zero order reaction? So for a zero order reaction, now our rate is still going to have units of molar per second equal to k, but a raised to the 0 power is just 1. And so it kind of leaves, and so for a zero order reaction, k's units let's write this out. K has units of molar per second. For our first order reaction, we had our rate, which is in molar per second, equals K, and then our concentration is molar. So when we solve for K, I should say we'll have some concentration of A molar. We solve for K. K has units of just 1 over seconds. What do you think the units are going to be for a second order reaction? So again, it's our rate has units of molar per second, K, and now it's A molar squared. So if we drive molar by molar squared, K has units of 1 over molar seconds. And then each of these could also be rewritten as
I noticed something weird in Alex too. When I was putting my rate expression, I put the multiplication dot between the molecules and brackets, and it wouldn't take it.
Yeah, it also complains because you can just type in times 10 raised to some power, and it doesn't like if you, because I always use an asterisk, right? Asterisk is a multiplication. It doesn't like using that multiplication sign versus an X for scientific notation.
Yeah, it was crazy. I kept going recheck, and I was like, "Why don't you try again? Why don't you try again?" I was like, "Just tell me what do I do?"
Yeah, that's weird.
Because I don't know.
That's weird. I can email them about that too. I guess they're trying to get you to use like the correct conventions, because by convention you use an X for scientific notation, and you wouldn't write multiplication between two things in brackets or parentheses. But yeah. Okay, so then this could keep going, right? Because we could have higher order reactions even. And so if you have a third order reaction, then it's molar to the -2, 1 over molar squared seconds, or 1 over molar cubed seconds, and it'll just keep going for higher and higher reaction orders. But again, because of collision theory, those become less and less likely because you need more and more things to be colliding at the same time. All right, so if we have a reaction, generic reaction A, converting to B, has been experimentally determined to be second order. The initial rate is 0.0100 molar per second. It has an initial concentration of 0.100 molar. Was the initial rate at A, the concentration of A equals 0.500 molar. If it's second order. Yeah, so we're increasing by a factor of 5. So then going from 0.500 molar will be our new concentration from 1.00 molar. So that equals a factor of 5. So we have to square that so that our rate is going to increase by a factor of 25. So then it's 5 times 0.01. My calculator's still in scientific mode. So 0.05. Wait. No, I typed something in wrong. I'm sorry. 0.25. Gotcha, kid's not in here. just to make sure I mention this, this is how you solve to get whatever K is going to be. But the units of K are such that when you multiply K by your concentration raised to whatever reaction order it is, your rate always has units of molar per second. So that's why the units of K change depending on reaction order, because rate always has to be molars per second. Constants sometimes can have funny units. So where are we at? Oh, we're doing great. Okay, so consider this generic reaction then. So I guess I got a little bit of my head ahead of myself when I was talking about those other those example reactions. But those are examples of reactions where there are multiple concentrations are affecting the rate. So for this generic reaction, our rate for the forward is proportional to the concentration of each reactant raised to a power. And again, these are experimentally determined. So we'll get to examples. So our rate then, these will each have a reaction order. It might be 0. So this could be, A could be raised to the first, and B could be raised to the 0. So then B doesn't actually affect the overall order. Hold on. Oh, what? I feel like this is missing. This should be in the slide. So the overall order is the sum of the exponents. So M plus N would give you the overall reaction order. So if we had a reaction that was experimentally determined that it was A raised to the 2, B raised to the 1, right, the overall reaction order for that would be 3. Unrelated, right? Unrelated, we can't pull that information just out of the stoichiometry. Again, you got to do the experiment. Okay, so the overall order, what would the overall order be for this first reaction given this rate expression, or rate law? 2. And then with respect to hydrogen, right, it would just be first order. So we do this overall equals 2. Hydrogen would be, yeah, first order, first, second. Overall rate for I2 also be first. And then for this next reaction, all right, our overall reaction is, yeah, third order with respect to just hydrogen. First order. And then for nitrogen monoxide, second. All right. So you can just read it straight off of the rate law. And notice too here that the rate order for hydrogen is first, even though there's a coefficient of 2 for hydrogen. Right? It's not related to, it doesn't come from the reaction equation, unlike equilibrium expressions. That's the next chapter. So the initial rate, this reaction was measured at several different concentrations with both reactants with the following results. So from the data determine the rate law we're going to determine the rate law and the rate constant. So how would we start this problem?
I would try out which one changes versus which one stays the same,
Mm-hmm.
and then figure out what's the order of respect to
Yeah, try and figure out the order with respect to that one. So you can do that with this first one. So our concentration of trichloromethane goes from, it doubles. So we can write in here that that's 2 times. So how much does that change by?
Almost.
Close enough to double. Close enough to double, right? So 2x. So is that what is the rate order then? Yeah, first order for trichloromethane. So we can start writing out a rate law. Rate is going to equal K, and we can do CHCl3. So that's going to be first order. And then for chlorine, which two experiments should we compare for chlorine? Mm-hmm. Second and third experiment. Because in the second and third experiment, the only thing that we changed was the concentration of chlorine. Sorry, so that doubles. And then how did that affect the rate of reaction?
So you increase by about 1.4.
So you take the 0.0098 divided by 0.0069. It gives us 1.4. Yeah, it's increasing by roughly 50%. So you can have other reaction orders too that are fractions. Not super friendly, and unfortunately that math doesn't work out super well, that it's 1.42. But that's the difference that's experimental data. The other thing we could do to figure out the reaction order for chlorine, although I think it's going to give us about the same thing, is we could take the natural log. This is from that equation that I derived earlier. So this will be our rate 2, so 0.0098. That's molar per second divided by 0.0069. I think this is going to give us a better result actually. And then divide that by the natural log of the concentration 2, so 0.020 molar over 0.010 molar. Crunching numbers. Yeah, that's better. So this equals 0. We only have 2 sig figs. So I guess we'd have to call this 5.1, but there you get that half. And that would be, just the reaction order. So, and it's unitless, actually, if you look at this, right? We're dividing molar per second divided by molar per second, and molar divided by molar, so that's going to be unitless. So 1/2 is the reaction order for that. So the overall reaction order would be 1.5. Usually I think this kind of thing arises from intermediate reaction steps. But again, we'll get to that. We'll get to that more later. So our rate law then is this. And now to solve for the rate constant K, we can just plug in the numbers from one of our experiments. And again, while you can use any of the experiments, I'm going to use the first one. So we'll have our rate as 0.0035. equals K times the concentration of trichloromethane no, it's going to be weird. So like, what is the unit? What are the units of this concentration going to be? Molar to the 1/2. Um, so it should be divided by 0.01 and then divided by 0.01 raised to the 1/2. So it's going to be 3.5 I think it's just, we're going to have molar per second divided by molar divided by 1.5 molar. So we are going to have 3.5 molar to the negative 1/2 seconds to the negative 1/2. Wait, sorry, not seconds to the 1. I don't think this is right. Right, because we're not dividing by, yeah. Questions? All right. I think. Okay, let's go over this one last example. So this reaction was experimentally determined to be first order with respect to oxygen and second order with respect to nitrogen monoxide. So we have diagrams that show here. The diagrams shown here represent the reaction mixtures in which the number of each type of molecules represents its relative initial concentration. Which of these would have the fastest initial rate? So if the yeah, how easy is that to see? Not super easy. These are all. I'm going to circle all the oxygens.
Would it be C?
Why is it C? This first order. Yeah.
I'm thinking because there's more molecules of the nitrogen monoxide and it has the biggest effect.
Mm-hmm. Yeah. Yeah, exactly. So because it's second order with respect to the nitrogen monoxide, that means any change in that concentration is going to be squared. Or any change in that concentration is going to square the reaction, the change in the reaction rate. So even though B has 4 oxygen molecules, right, that's only going to be to the first power. And C will be to the second power. So if you wanted to, for whatever reason, you're making nitrogen dioxide in like an industrial process, you'd want to try and get as much nitrogen monoxide in there because that's what's going to speed up your reaction the most, right? You'll be able to produce more by adding that nitrogen monoxide. Meanwhile, changing the oxygen concentration is not as going to have as much of an effect. Look at that. That's great. We're right on track. Okay. I should have downloaded this onto my iPad. I do have a few more. How many of you guys are like done with that, the Alex modules already for this week. Actually, I should know that. I can look it up. That's fine. I get it. Okay. This was another one that I wanted to go over. Let me download this real quick. Because now we can just go over questions, or we can go back and go over stuff because we've gotten through as much material as we need to get to. My hope was to print out these questions and then hand them out to you guys, and then we could go over them. But didn't get to that. Now this is being a pain. 2022 fall, Chem 2. Wait, worksheets. No, that's. We can take a look at these actually. Well, that imported beautifully. Oh, I'm sorry. This is just. I have no idea where I saved it. Where are you? Oh. Still not fantastic. Okay, this is the problem specifically that I wanted to, the problem type that I wanted to go over with, because this one seems a little overly complicated to me for what it's trying to get you to do. So we have a reaction, and because we have, I guess we don't have that much time. I'll just go over it so you get a look at it. So we have a reaction between methane gas and steam produces carbon monoxide gas and hydrogen gas. If a reaction consumes 382 liters per second of methane gas at this temperature, 264 degrees C, 1.89 atmospheres, what is the rate of hydrogen production in kilograms per second? This is the kind of question that I would put on like the final for Chem 20. So it should include topics that you have, but where do you start with a problem like this? Write an equation, chemical equation. So we got methane gas, CH4. Steam is water. And we should put these in. And we're producing carbon monoxide and hydrogen. Cool. Now balance it, right? How should we start balancing this one? 3 in front of hydrogen, yeah. And then it's balanced, right? Cool. So what's next? Yeah, so well, we want to know how much, we want to know the rate of hydrogen production. The only thing we're given information about is methane. Oh, I see what you're saying. Yeah, moles consumed of methane. So we're starting with CH4. So how do we get moles of CH4 though? It's an ideal equation to use. Ideal
gas law.
Yeah. So PV equals nRT. So we can plug in our pressure, 1.89. We'll get Celsius to Kelvin. Solving for moles, 0.0821 atmosphere liter per mole Kelvin. And yeah, then times our temperature, 264 degrees C. Just to work this out beforehand. Oops. So we're going to have 1,637.14 moles of CH4. So what's next? We want to get to hydrogen. This is actually moles per second. Yeah, stoichiometry. Moles to moles. Moles of what to moles of what? So how many moles of hydrogen for how many moles of CH4? 3 to 1. I guess this is a review question. This is pretty good because it's really covers a lot of topics at the same time. Okay, so that's moles per second of hydrogen. How many kilograms of hydrogen? Yep. So 4911.42 moles per second of H2 times 2.02, because it's H2, grams per mole. And then we'll have to go to kilograms. So to go to kilograms from grams, what was that? Divide by 1,000, move 3 places. 3 places. Yeah, so 9.921. So we take this, divide by 1,000. Cool. Kilograms per second. H2. How many sig figs? Yeah. So really 9.92. So yeah, that's in there for the review. All right, well, that's 921. My hope is that